Hello, precalculus class. Today you're going to have a lesson on a number of different application problems using conic sections. Go ahead and first try the warm-up about circles. You can pause the video here. All right, here is your answer. It's right down here. What I did first was draw myself a sketch. I plotted the center at 3, -4, and I plotted the point on the circle at 1, 1. We know the distance between these 2 points will be the radius of the circle, and the circle looks something like this. I can continue that around. So I used the Pythagorean theorem to find the radius. The radius squared equals 2 squared plus 5 squared. I found these lengths by looking at the differences in the x's and the differences in the y's. So the radius squared is 29. Well, I don't even need to bother to take the square root because the equation is x minus the x coordinate of the center plus y minus the y coordinate of the center equals radius squared. And that's your answer. All right, so here's your first application problem. We're going to do one of circles, and then we're going to look at a couple of ellipses and a couple of parabolas. I left off the hyperbolas, and that we're not going to look at those applications in this unit. Go ahead and read through this example, pause it here, and then we will talk about the solution. Okay, here's your solution and what you had to do. First thing I did was draw a sketch. Here's your picture of the Earth with the center of the Earth, and I just marked in the radius of the Earth, which we don't know what that is yet, and the satellite is going around the Earth 0.6 units above the Earth. So its center of rotation is also the center of the Earth. So the first thing I did was I took the equation we were given and I completed the square on it so that I could find this value here. That value is the radius squared of the Earth, since the surface of the Earth was this equation. So if I square root that, I get 64. That means the radius of the Earth was 64 units in this problem. Well, the satellite's radius from the center is 0.6 added to the 64. So that's the r I'm going to use in my new equation. When I square it, I get this, and we have our answer right here. So it has the same center, -1, -2, and it has a new r squared value. I did go ahead for the purposes of the problem and put it in the same format, your general form, as well by just foiling out these two binomial squares and then combining like terms, and you get this. I think for the purposes of the problem, though, we can leave it in standard form. All right. All right, here's the next problem. Let's just read this together. In a whispering gallery, a person standing at one focus of the ellipse can whisper and be heard by another person standing at the other focus of the ellipse because all the sound waves that reach the ceiling from one focus are reflected to the other focus. Where in the hall are the foci located? So we're looking for where this person is standing and where this person is standing. Just so that you can see, this is a semi-ellipse in that you could kind of continue the ellipse down here, and this is your major axis, and this is your minor axis. So they give you a whole bunch of information, and what we're going to do is we're going to actually write the equation of this elliptical shape and then use it to find the location or the value for C, because C is the distance from the center to the foci, and that will answer our question. So the first thing I see is this is longer in the horizontal direction than it is taller in the vertical direction. So this is a horizontal ellipse, and we know if the distance from the edge to the edge is 50 feet, then A is 25 feet from the center to the vertex. And B is 20 feet. You really don't have to worry about this 6 feet because it's just kind of saying that's where the people are talking, kind of like their height or to their mouths, where they would start their whispering. So you can pretty much ignore that. and b, which is the distance from the center to the co-vertex, is 20. So based on that, we're going to put the center of our ellipse right here in a coordinate plane at 0, 0, which makes the equation much easier. And really didn't ask for an equation, but I'm going to provide it anyway. We know x minus 0 squared is x squared. And since it's horizontal, I put the 25 squared underneath. And then it's an ellipse, so it's plus the y minus 0 squared over the 20 squared. And an ellipse always equals 1. There's our equation. Now let's finish the problem though. We need to find c squared. So we know that a squared equals b squared plus c squared in an ellipse. So a squared is 625 and b squared is 400. So we have c squared equals 225, their subtraction, and c is 15. So what we have here is it is 15 feet from the center to where the foci is located, or you can argue it's 10 feet from the edge of the wall. And you could respond either way to explain where in the hall are the foci located. So that's an elliptical problem. All right, this next example is about a parabola. Let's just read it together. A satellite dish is shaped like a paraboloid of revolution. The signals that emanate from a satellite strike the surface of the dish and are reflected to a single point. This is the focus of the parabola where the receiver is located. Let's just kind of look at a picture of that. So I'm going to kind of draw a satellite dish. Now I'm doing mine at an angle, and when we solve this problem, we're going to make it either vertical or horizontal. And what's going on here is signals come in, they reflect on the parabola of revolution. So actually think about this as a salad, as kind of you're rotating and you get this whole paraboloid of revolution. So kind of you're rotating around and you have this dish. That's the best picture I can have. But as the signals come in, they're going to reflect off the parabola and reflect to a single location. And this is the structure nature of a paraboloid of revolution. And this point here is called the focus. So let's just make that picture a little bit better. So there's the paraboloid. And these are the points coming in. And there's the focus point. They all hit the dish and reflect back to the focus. And vice versa. If you have a signal or even like a light source emanating from that foci, it will reflect against the parabola and come out at a straight angle out. All right, now let's draw this so that we can solve this problem and look at the facts. So I'm going to draw a parabola here, and I am going to place, since in application problems you always want to place the vertex or the center at 0, 0 in the coordinate plane to make your equation much easier. I'm going to do that. So now let's read the rest of the problem. If the dish is 10 feet across at its opening, so this right here is 10 feet, so this is 5 and this is 5, and it's 4 feet deep at its center, so I didn't draw this very well or to scale, but that's 4 feet. That means this ordered pair right here is 5, 4. And all we know is this is a point on that parabola. We don't know where the focus point is. We don't know the equation of the parabola. We do know the center. So we're going to actually write the equation with as much as we know at this point, because they want to tell it, we want to find at what position should the receiver be placed. We want to know where to place the focus point. So what we need is our p value, because if you remember in a parabola, p is the distance from the vertex to the focus. So this is a vertical parabola, and that means it's an x squared, and the vertex is at 0, 0, so that's x minus 0 squared equals 4p y minus 0. So that's y. And now what I'll do is I'm going to use the point on the parabola, 5, 4, and plug it into this equation for x and y and solve for the p, and then have my new equation of this parabola. So x is 5, that's 25, x squared, and y is 4. So we have 25 equals 16p, and I divide both sides by 16. So I end up with p equals 1.5625. Yes, we can round it. Is my value of p. So what that tells me is the distance to the focus point. If this is 4, it's about right here is my focus point. And this is 1.56. And in this case, since we're talking feet, this is feet away from the vertex. And that's all you needed to find. We can, though, rewrite the problem here. If we want, we can write x squared equals, let's see, it's 25 fourths y. What that was is it was 25 times 16 is p in fractions times 4. So you end up with 25 fourths y. So we'll leave it like that. You didn't need the equation, but it was nice to add that in. But the real answer is what the p-value is. This next problem is another parabola problem. So let's read it together. A bridge is built in the shape of a parabolic arch, and it is to have a span of 120 feet and a maximum height 25 feet. Find the height of the arch at distances of 10, 30, and 50 feet from its center, which in this case, the center is going to be its vertex. So let's draw a little picture here. So, you know, if you've ever been on the Merritt Parkway, the bridges kind of look like this. And here's the roadway up top, or you could even have the road going through. So the parabolic arch is this shape right here. So let's figure out, so I guess first of all, you can see this parabola is opening down, but it is a vertical parabola, so it's going to be an x squared, and p is going to be negative since it's opening down. So I'm just going to write down x squared equals 4py, because we are going to make the vertex at 0, 0 in the coordinate plane. All right, let's look at this. So here is the ground, and it's to have a span of 120 feet. So that means it's 60 feet in each direction. And so this is 60. And then it has a maximum height. So this distance here is 25. Well, since this is opening down, this ordered pair is actually 60x over and minus 25. And that's going to help us make sure that p becomes negative. All right. So once again, like the last problem, I don't know the p-value, but I know it's negative, but I have a point on my parabola. So what I'm going to do is take this equation and plug in my x and y. So I'm going to have 60 squared equals 4p times negative 25, and we can solve for p. We get 3600 equals negative 100p, divide by negative 100, and we end up with p equals negative 36. All right, so p for this shape, which is kind of odd, it's actually down here in the ground, because if that's 25, it's actually a distance of negative 36. But that's okay. Let's now write our equation. So x squared equals 4 times negative 36, which is negative 144y. And now we can use this equation to find the answers to our question. They want us to find the height of the arch at distances of 10, 30, and 50 feet from its center. So if this is 60 feet away, we need to go 10, 30, which is halfway, and 50. So we're going to actually plug in values of x at 10, x at 30, and x at 50. And we will get negative, right? Because we're going to have this point here, in this point here, and all we need to do is add those negative values to 25, the maximum, and we'll get the height at the different places on the arch. So when I plug in the equation 10, we're going to end up with 100 equals negative 144y, and y equals negative 0.69. When I add that to 25, we end up with 24.3 feet. And I'll do that same thing for both x of 30 and x of 50. When you plug in 30, you're going to get 900 divided by negative 144, so y equals negative 6.25. Add that to 25, and now the bridge is a little bit shorter. It's 18.8 feet. And lastly, kind of at the outer edge of the bridge, if x is 50, we'll end up with y equals negative 17.4, which means the bridge is only 7.6 feet tall. So I don't know whether you know, but the Merritt Parkway does not allow trucks on it, and a lot of it has to do with the height of the bridges. The bridges are too short, especially on the outer edges, for a truck to pass safely underneath. But these are your three answers right here. So that is a parabola question. You could have a similar kind of problem using an elliptical arch as well. All right, this is our last example problem. This is about an ellipse, and we have a racetrack in the shape of an ellipse. So I'm going to draw a picture of a racetrack, and it says it's 100 feet long and 50 feet wide. So I'm going to put the center, of course, and this will be my coordinate plane. This will be 0, 0. And like we said, it's 100 feet long. So this is 50 and 50, and 50 feet wide. So this is 25 and 25. Now the question says, what is the width 10 feet from the side? So when we finally answer our question, we're going to be interested in this length here when this is 10 feet from the side. So how wide is it 10 feet from the side? So the first thing I want to do is write an equation for this ellipse. And what's so nice is we know the a and b values already. We also have decided that the center is at 0, 0. So let's just write it down. X squared over a squared, which is 50 squared, plus y squared over b squared, which is 25 squared, equals 1. That was pretty easy since it was a horizontal ellipse. So what I'm interested in finding is the height of the ellipse. So, or maybe this ordered pair on that ellipse, which is going to be 40 over, and I need to know how tall it is at that point. And then I can just double that answer to get the width at that point. So what we're going to do is plug in an x of 40. So we're going to have 40 squared over 50 squared plus y squared over 25 squared equals 1. And to solve this equation, you really need to square each of these values. And then you're going to do y squared equals 1 minus the 40 squared over 50 squared, and multiply that whole quantity by 25 squared. And that's how you isolate the y squared. We end up in this problem with y squared equals 225. How nice. And that means y is 15 feet. So this is a 15, and this is 15 tall, 10 feet from the edge. So that means the total width is 30 feet, or just double the 15. And it's 30 feet wide. That is that problem. And that's the last of the sample application problems. We're going to do a little bit more talking about rotation of conics to end this lesson. All right, take a look at these notes. Here is the general equation like we've been working with all along. But notice we have never dealt with this bxy term right here. All of our conics have had the b coefficient be 0. And so what that means is when b is 0, those conics are aligned directly vertically or directly horizontally. Notice we never had an ellipse that was at a 45-degree angle. It was always just straight up and down or straight right and left. So what happens when b is not equal 0, it means the alignment axes are rotated. And we could spend a lot more time using trigonometry to find the equations of rotated conics. Now, we're not going to do that, but I do expect you to be able to deal with and understand which conic we have when we have a bxy term. So take a look at these notes here. If the conic is not a degenerate conic, then you can find the discriminant. So we've seen a discriminant before when we talked about quadratics, b squared minus 4ac. It's still called a discriminant, although the b and a and c coefficients are very different than when it was just a parabola or a quadratic equation when we studied it in Algebra 2. But we can just look at this discriminant value from this general equation, including the bxy term. And if it's less than 0, we have an ellipse when a and c are different, or a circle when a and c are the same. If it equals 0, then we have a parabola. And if it's greater than 0, we have a hyperbola. And that's all there is that you need to know about this. It's just understanding that the rules when we didn't have a bxy term are different than the rules when we have a bxy term. So that's something very important to note. All right, on the next slide, you're going to do a few examples. So here we have a bunch of equations of conics, and notice that each of these have an xy term. So the old rules do not apply. These are all rotated conics. But which conic sections are they? So what we're going to calculate for each one, and I'll do the first two examples for you, and then you can do the last two on your own, is to calculate b squared minus 4ac. So on example 1, b is 1, because that's the coefficient of the xy term. So we have 1 minus, there is no x squared term, which the coefficient would be a, and no y squared term. So that means 1 minus 0, which equals 1. And 1 is greater than 0. So this is a hyperbola. Feel free to go back in the slide to look at the formulas again. Greater than 0 means it's a hyperbola. All right, let's look at the second one. So here, once again, we're going to calculate b squared. So b is negative 5, so that's 25, minus 4 times 4a times 16. And that value, 25 minus 256, 16 times 16, is very small. It's definitely less than 0 because it's negative. So when it's less than 0, we have an ellipse or a circle. Now, this is an ellipse, and the reason it's an ellipse is because the a and the c are two different values. If they were the same, this would be a circle. Why don't you pause the video now and try to determine what kind of conic we have for questions 3 and 4, and then you can unpause the video and find out if you were right. All right, and here are your answers. Number 3, b squared minus 4ac ends up being 0, so you have a parabola. And in number 4, b squared minus 4ac ends up being negative. It's 144 minus 256, which is less than 0, which makes you think an ellipse or a circle. But because a is 8 and c is 8, they are the same value, so it's a circle. That is it for our lessons in conic sections.